Good afternoon, everyone. Our speaker for day 2, session 4 is Dr. Suchandan Pal, Chief Scientist and Group Head CSIR CIRI, renowned for research and academics in optoelectronics. Now, I would like to request FDP coordinator Mr. Rajesh Singh Shekhawat to welcome our distinguished speaker with the bouquet. Dr. Suchandan Pal received his BTech and MTech degree from Institute of Radio Physics and Electronics, University of Calcutta, Kolkata in 1992 and 1994 respectively. He joined CSIR CIRI Pilani as a scientist in 1955. In 2001, he was awarded the Commonwealth Scholarship and pursued his PhD at City University, London, UK, in the area of fiber Bragg gratings, optical-based fiber sensing and instrumentation. He returned to CIRI in 2004 after completing his PhD. Presently, he is leading the Optoelectronics and MOEMS group. He holds a position of senior principal scientist as CIRI and a professor in ACSIR. In addition to the area of FBG, his present research interest lies in the area of integrated optics involving with the design and technology development of various passive photonic components, waveguide gratings, and GAN material-based LED device. He has led a few government-sponsored projects of national importance. He has authored and co-authored over 100 scientific and technical papers in various reputed national and international journals and conferences with a total 1,426 citations. He served as a reviewer for various national and international journals like IEEE Photonics Technology Letters, Review of Scientific Instruments, Sensor and Actuators, Physical, Optic Express, Optical Engineering, and so on. He was a member of Institute of Physics, UK 2003 to 2013. He is a life fellow member of Optical Society of India and the Institution of Electronics and Telecommunication Engineering, an Institute of Engineers, and also a member of Indian Physics Association and Semiconductor Society of India. Now, without a further delay, let us warmly welcome to the stage Dr. Pal, who will be sharing his expertise. Sir, please.
Thank you. Okay, I understand that this is the fourth lecture, I think, on day 2nd, isn't it? On semiconductor excellence, unveiling, design and development. It is in hybrid mode, obviously, so we'll interact whoever present here, and you can take questions whoever in the online, and we can go ahead. So today I will discuss about the semiconductor and photonic devices and the overview on design, fabrication and characterization to some extent. I will give an overview, and because each and everything discussion may not be possible, and I think in last 2 days you have gone through a little bit on semiconductors as well. So maybe it is a bit different from earlier presentations. So I understand they have covered all over areas of semiconductors. So before the start of my presentation, I just very briefly introduce about my organization, whoever not familiar with the organization. This is CSIR CIRI, Central Electronics Engineering Research Institute in Pilani itself, and this is one of the 37 laboratories of CSIR. CSIR is Council of Scientific and Industrial Research, And the institute is working in the area of mainly electronics engineering. And this is the location all we know in Pilani, and all the 37 laboratories of CSIR are spread all over India. And this is the front view of Siri. Whoever visited already Siri, they know. And the working area particularly in the area of semiconductor devices and systems, vacuum devices or high power microwave electronic devices and systems, and electronic systems and instrumentation, based on whatever devices we are fabricating in the area of semiconductor or high power microwave, or whatever available in the ready-made market, we can go for that systems as well. We are having the headquarters in Pilani, and we are having centers in Chennai as well as Jaipur. They are also working in the area of electronic systems instrumentation and to some extent standard calibration. So with this introduction of my organization, I just start my presentation. I will give the outline of the presentation, introduction to semiconductors and integrated optoelectronics, because optoelectronics again is a part, some portion can be overlapped with semiconductor, again semiconductor some portion will be overlapped with optoelectronics. So I will cover both semiconductors and optoelectronics portion as well. What I will do in first talk, although this is only one talk itself, integrated one talk. In first part, I will discuss about the semiconductor device, and I will go for one specific semiconductor device, say LED, and its design aspect, fabrication, characterization aspect. And in the second part, I will cover some of the integrated optoelectronics components, mainly passive components, and I will again focus one of the passive component on optoelectronics and its design, fabrication and characterization aspect. And obviously whenever we fabricate some of the device, we design or we fabricate, efficiency is one of the major portion. Because whatever we want to fabricate the device, we want maximum efficiency of the device. So how we can achieve that, we'll discuss not only in terms of design, but also in terms of fabrication as well. So various aspects are there we'll discuss, and we'll discuss some of the specific areas, some devices, what we have designed and what we have fabricated in our institute itself, and some recent trends, and I will conclude. So very first, I'll just go through just the evolution of photonics, optoelectronics, and to some extent semiconductor. 1837, that is the very start of the communication, when telegraphy was invented, and it was invented by Samuel Morse. And telegraphy, it was speed was high, but data rate was low. There was few codes, and those were being transmitted from one place to another place. As the speed was low, so in our earlier generation, maybe 20 years, not 20 years, more than 25 years back, we got some telegraphic information in terms of very crisp code through post office, we understand. So now it is all vanished, because after that email has come, everything, now WhatsApp, everything, it is now the area of information and high speed information. So speed is one of the criteria now. So that was the starting of the communication. And that is the necessity from where the semiconductor, invention of semiconductor was there. And then 1878, another milestone, Alexander Graham Bell, he invented the telephony. And that was also moderate distance communication at that time. I just very quickly, I'll go through, otherwise I cannot cover my whole topic. Then, in the same year, 1878, James Maxwell, he gave Maxwell's equation. That is a great invention, particularly theoretically. And from that Maxwell's equation, there are 4 Maxwell's equations, all communication part, electromagnetic radiation part, those can be explained afterwards. Then 1888, Henry Hertz, he demonstrated the radio waves based on Maxwell's equation. He demonstrated first. And then 1895, Marconi and J.C. Bose, they demonstrated the radio communication based on the electromagnetic waves. And J.C. Bose was the first Indian, and at that time itself, nowadays it has been shown from the literature that J.C. Bose first coined the term semiconductor, and he invented the semiconducting property in some of the materials. So he's the first person to conduct with semiconductor. Then research towards for better and faster communication, towards higher speed communication means obviously you need higher carrier frequency, and obviously you need bandwidth. So more and more bandwidths are required, and higher and higher carrier frequencies are required. So from those requirements, then invention of radio waves. So that was in the radio telecasting, where the bandwidth was very much limited, around 15 kilohertz, and where carrier frequency was also very low, around 0.5 to 2 megahertz. Then TV came into account, where the signal in terms of picture and voice were transmitted. So obviously the bandwidth is required is more. Here the bandwidth was around 6 megahertz, and carrier frequency obviously much more, around 100 megahertz. And whenever we go for that requirement of higher and higher carrier frequency, obviously the carrier signal we need, if we check the frequency increase of the frequency of the carrier signal, it is going towards the optical signal. So the invention of then radar and satellite, 1940, then 1960 invention of first laser, and which is in hundreds of terahertz range. Nowadays also terahertz communication and terahertz devices, various terahertz devices are very much important, and research are going on. But during that time, 1960, that was the first invention of ruby laser, first, with wavelength of 694 nanometer, which is visible. Then helium neon laser, again in 633 nanometer. That was bulky in size. And after that, the semiconductor laser was first invented in 1962. And semiconductor laser, obviously that is very much compact. But if we need high power of intensity of laser light, semiconductor laser may not serve the purpose. Nowadays, obviously, researches are also going on to for higher and higher power of semiconductor laser as well. But at that time, 1964, carbon dioxide laser was first invented. Again, that was by Kumar Patel from one Indian, and for high power laser. So if we go for that terahertz range, so bandwidth obviously will be high bandwidth. So communication, there will be no problem. But there will be problem for the combination of electronic and optical components. Because when you transmit the optical signal through optical components, the speed of the signal is very high, but the electronic signal is not that much. And if we want to transmit the signal, optical signal guided way, at that time there was no proper guidance or waveguide to propagate optical signal from one point to another point. During the period of 1966, Charles Cow, he invented the first optical fiber, first glass and then optical fiber, and it was then commercialized in 1970 by Corning Glass Company, fiberglass, and at that time the loss was 20 dB per kilometer, and now the loss in optical fiber is less than 0.2 dB per kilometer kind of thing. So that much has been improved nowadays. So obviously emphasize to integrate optoelectronics, integrated optoelectronics, which can control the light with ultra short pulse. So use the light to perform the function within the domain of electronics. So that is the main purpose of optoelectronics, and the devices are being used in the area. Those are the optoelectronic devices. And the photonics, what we are calling nowadays, that photonics term was first coined in 1980 by IEEE Bell Lab. If we check the optoelectronics area, that can cover huge areas. Basically, it is the electromagnetic theory that is the main thing. And in application in the area of nonlinear optics, laser physics technology, ultra-fast high-power laser diode, optical fiber technology, remote sensing technology, in various aspects of biomedical optics, fluorescence imaging, imaging science, optical storage, everywhere we can see the optoelectronic devices, and most of them are made by the semiconductor materials. And if we see the wavelength wise, that these are the increasing wavelength range in that. So wavelength increasing, that means the frequency increasing in that way, opposite direction. And for the optical communication, what we use that in visible and to some extent near infrared region for optical communication, and for microwave other portion, microwave communication in that range, in that range, IR range, and terahertz communication in this range. So all those things. And earlier that radio waves propagation in that AM and FM through radio waves were there. So all those wavelengths of the electromagnetic radiation spectrum were used. Now, although this is just in part of photonics optoelectronics, so if we see that what are the photonic or optoelectronic devices are there, and what is the purpose? The purpose is generation, emission, transmission, amplification, detection, modulation, sensing, switching of light, including laser, diode, LEDs, photodetector, optical fiber, and various other components as well. And all those components or devices may be optical fiber based or optical waveguide based. If it is optical fiber based, so all fiber component will be there. If it is waveguide based, this is integrated optics, or if the material is semiconductor, then integrated optoelectronics by semiconductor material. There are two types of devices, active and passive. Obviously for generation of light, modulation, everything will be active, and there are various passive devices and components are also being used depending on the requirement, whether we need hybrid circuit, whether we need monolithic circuit. So within the same material itself we can fabricate, we can design and fabricate the source, waveguide, detector, everything. So those, depending on the requirement, we can go ahead. So we have discussed the fiber-based, waveguide-based, and active and passive. And what are the basic or fundamental parameters? So if we just check the communication portion, one is the source from where the signal is being transmitted to destination. and that is done by detector, and from source to destination it is propagating through open medium or guiding medium. So one is source, the other is detector, and third is the medium through which the signal is propagating. And there are various parameters for source, detector and medium. Briefly, that emission, what is the emission wavelength, what is the spectral width, what is the bandwidth of that one, what is the optical power, what is the effective emissive area and radiation pattern. All those are the fundamental parameters for the source. For detector as well, the parameters are responsivity, sensitivity, operation wavelength and speed of response. And the medium parameter, if it is optical waveguide, so then core and guide size and shape. What is the index? Here refractive index is one of the main parameter, and that profile of refractive index is the major thing. And what is the bandwidth, what is the attenuation of that material, what is the numerical aperture, all those parameters. Now if we consider that 3-nitride, particularly 3-nitride semiconductor optoelectronics, and there the optoelectronic of all the devices or materials, semiconductor and 3-nitride. So how 3-nitride, we will discuss in next slide. 3-nitride means if we go through the periodic table, so group 3 component and group 5 component will be combined there. So nitrogen is common there. Nitride means nitrogen is there, and that is the common in group 5 we are considering. And group 3, various group 3 components we are considering, and those semiconductor based devices in the area of optoelectronics that can cover. And that is one example, and that can go for wide range of applications in the area of photonic optoelectronic integrated circuits, solid state lighting for LED or laser, display technology again with using LED and laser, visible light communication again with LED and laser, detector, disinfection, sensing, monitoring application, quantum information processing technology, all these things. Now here, just one example, that if we consider that gallium nitride based material, this is one of the major semiconductor material, and if we check the very fundamental semiconductor material starting from silicon, germanium kind of thing. So those are the elemental, very fundamental semiconductors. But if we consider there are various compositional semiconductors are also there, just like gallium arsenide, indium phosphide, gallium nitride is also one of those. If we consider the electronics optoelectronics property, that means optoelectronics means if we drive with electrically drive, and then optical output will be there in case of LEDs or lasers. On the other way, for the detectors also, if light falls on the devices, proportional current will be at the output, in the case of solar cell as well. In those cases, when the interaction or the conversion from light to electricity or electricity to light, then the radiative recombination matters. Because from electrical to light, optical signal conversion happens due to the electron-hole recombination. Again, semiconductor means there are valence band and conduction band. If we energize those semiconductor, the free electron from the valence band excited to conduction band, and after certain time, these so that will form hole in the valence band, and after certain time, these electron and hole combine each other. So this is called electron-hole recombination. When those recombines electron and hole, and that emits certain energy. And those energy may be in the form of radiative recombination, this recombination in the form of radiative or non-radiative. So if it is in the form of radiative, So maximum portion of the energy will be emitted in the form of light. If it is in the form of non-radiative, then some portion will be converted in terms of heat. So in this case, we need maximum efficiency when we consider maximum energy of electricity or electrical energy will be converting to optical energy without heat energy kind of thing, or vice versa in the case of detector. Or now how we will increase those efficiency we will discuss again. So here also that gallium nitride, if that base material, and we can introduce that aluminum composition as well as indium composition. So this is the binary semiconductor gallium nitride, two elements are there, but if we incorporate aluminum in composition, so it will be algan. So certain composition of aluminum will be there in gallium nitride. What will happen? That gallium nitride is having certain band gap. Here we see that this is the lattice constant of that semiconductor, and that is the band gap. So gallium nitride is having band gap of around 3.4 electron volt here. But if we incorporate aluminum composition, the band gap of this material can change up to 6.1 electron volt. So where gallium is 0 and aluminum 100% composition, so this will again, it will be binary composition, so by aluminum nitride. Otherwise, certain composition Lx, gallium 1 minus X nitrogen kind of thing. Where
if it is like if there is a band gap is near about 6 electron volt, normally it is an insulator. So how we will categorize that aluminum nitride is a kind of a
category?
Semiconductor?
Yeah. So it is mainly categorized in the form of, somewhere in some books it is mentioned that if the band gap is more than 5 electron volt or 6 electron, somewhere it is 5, somewhere it is 4, somewhere 6 kind of thing. But with this composition, generally it can be considered as semiconductor with high band gap. So we can consider it is high band gap semiconductor. So there are various applications.
It's like an ultra band gap semiconductor.
Ultra high band, high band gap semiconductor. Insulator, there will be one criteria is that band gap is very much high. But in terms of free electron, electron hole pair recombination, all those we have to check. So those properties will be fulfilled or not. So here we will consider those are the high band gap semiconductor. Just nowadays, various high electrical vehicle and high power amplifier, all those applications are they require very high band gap material. So algan is one of the promising material for that one. So from the high band gap, so if the band gap is very high, from the band gap itself, we can estimate what is the emission of wavelength if we want to convert that, suppose LED. So we are driving that one, giving electrical signal, and we are getting the optical signal. So corresponding to that band gap, 6 electron volt will corresponds to, we can estimate that one, 1.24 divided by Eg, we can consider that one. And it will be around the UV range. So if aluminum composition less and less, so it will come towards the visible side. So this corresponds to, this is the band gap in EV, and that corresponds to the emission wavelength in terms of lambda nanometer. So you see here 6.1 electron volt corresponds to around 200 nanometer, which is UVC or extreme UV you can consider. So you can get that emission itself. So if we want to fabricate a UV LED using gallium nitride material or algan material, it is possible. But at present also, this is also area of contemporary research, because it is theoretically possible and efficiency nowadays again below 5%. And if we go higher and higher towards the UV range, the efficiency goes lower and lower. So much more difficulties there. Unless we have some breakthrough, or it is very difficult to get on that high efficiency UV light. But in the visible range or near UV range, obviously it is very much useful. And we are getting useful obviously in the high UV range also it is very much useful, but in terms of efficiency, now just like for sanitation purposes, everything, so mercury based light, UV light are being used. But the main problem of mercury light is that is very much hazardous, so that is not environment friendly. So people are, researchers are going for the solid state lighting. But that's why we have to go for that higher efficiency for that. Similarly, if we incorporate indium composition, so band gap will be lower and lower, but still all those are the direct band gap. So lower and lower, and starting from that visible range towards green range also it is possible. Again, high indium incorporation within that material, that is also technological challenge. So beyond very infrared, it is very difficult to get the emission in that wavelength using gallium nitride or indium gallium nitride based material devices. Nevertheless, other materials, gallium phosphide or gallium arsenide phosphide, all those materials are very much efficient to emit the wavelength in that range. So what I was mentioning that this is the third group element, boron, aluminum, gallium, indium, and nitrogen is the common. So that's why it is called third nitride devices. And this is again, we are repeating this picture. Gallium nitride is the base material. If we incorporate aluminum, then algan in this line, this is the extreme aluminum nitride. If we incorporate indium, this is the extreme indium nitride, and in between indium gallium nitride. So this is the visible portion in terms of band gap, and this is in terms of wavelength as well. This is lattice wedging. And the areas of applications huge: deep UV LED laser, solar blind detector, gallium nitride based HEMTs, high electron mobility transistor, LEDs, photovoltaic solar cell, all applications are there based on that material. So all those things. I just skip that one, that based on that, where are the applications are there in LED and lighting, these are the applications. AP structure or growth of that material is this one, laser in this area, power devices nowadays, it is covering that one, MEMS and sensors this area we'll consider. So now why we are going for the integrated? If we consider the applications in the area mainly in communication and sensing, so if we go for that integrated, that will obviously give the compact device. So that is one of the things. The other is if we go for integrated material, we have the flexibility in terms of material and in terms of size and shape of the waveguide. So we'll discuss how it, because it is integrated. Material means whatever what I discussed, that gallium nitride is one of the material. Changing aluminum composition, we can change huge other material. Indium composition, you can use other material as well. And if we make the device may have different size and shapes, and for signal transmission from one point to another point, if the waveguide, if we fabricate, the size and shape of the waveguides also may be of a different shape and size. So in terms of that, that flexibility is also there. And the various sensing applications will be there. And if it is integrated, the other advantage is that for mass production. Because if it is integrated, we can fabricate the mask, and after fabricating the mask, we just go for the production of very small chips in various wafers. And in one wafer, maybe hundreds, maybe thousands number of chips will be fabricated depending on the size of the devices there. So mass production may be possible depending on if it is integrated. And if it is integrated, obviously, the stability of the structure will be much more. Just if we compare, if it is optical fiber based, it is very much brittle, and it is very much sensitive to bending, twisting, everything. So here, if the material is stable, if it is integrated, the stability of that device is very good. Very small, you can introduce within the body structure itself, for if the material is compatible to human material, that can be used for biosensing application as well in various ways that can be. So now we can go for, this is a typical example of that integrated optoelectronic devices or integrated photonic circuits. So within this wafer itself, there may be various devices, and those may be laser, directional coupler, optical amplifier, various modulator chips, waveguides everywhere. So there, switches, diodes, laser, everywhere, everything is there. And if those devices are made of the same material of the substrate, so it is called monolithic, otherwise it is called hybrid. But the thing is, if it is integrated, how to communicate with the outer world? So to communicate with the outer world, the common practice is to use the optical fiber getting connected with that one. And in this case also, the connecting the optical fiber with those waveguides, so which is giving in the input section or output section, is also very much critical, because the alignment of this waveguide to the optical fiber in the input section as well as in the output section is very much critical. So we have to take care of that one also. And in the waveguide as well, we have certain properties that we can go for the chemical etching, so that 45-degree or 54-degree angle cutting will be there. So that in that cut itself, the optical fiber can be placed, and the thickness of the waveguide and the width of the waveguide we can design and we can fabricate, which is compatible to the optical fiber core region. Now, efficiency, if we term, what are the various terms of efficiency, and if you consider if it is LED, that means light emitting diode. In case of detector, it is just opposite, because in case of detector, the light is input and the electrical signal is the output. In case of LED, electrical signal is driving and output signal is the light. So there are various efficiency terms, and if we start from this bottom, first is the injection efficiency. Second is the internal quantum efficiency, then light extraction efficiency, then external quantum efficiency. What are those? That if we drive some electrical signal and one device is there, suppose this is the device cross section. We are giving the input from this side, and in between there will be some active region where the light or electron hole recombination will take place, and the other side is the output. So electrons are being injected from that side, and active region in between somewhere. So some of the electrons may not reach to that active region itself. So the number of electrons injected in the active region per second with respect to the number of electrons injected in the LED input. So that is the injection efficiency. And what is internal quantum efficiency. So some of the portion it is going to the active region. Those are the responsible for giving the electron hole recombination, which is responsible to give the photon or radiative recombination in terms of radiation of photon. So it gives the number of photons emitted from the active region per second with respect to number of electrons injected in the LED per second. So, and from there, other term is there that light extraction efficiency. So light is being generated within the semiconductor material itself, but in some cases in LEDs what we need the light output out of the device. So whatever the light is being generated within the device, we need light output out of the device. So number of photons to free space per second with respect to number of photons emitted from the active region per second. So this is the overall external quantum efficiency, that is the number of photons emitted from the free space per second with respect to number of electrons injected into the LED per second. So if you multiply these terms, injection efficiency, internal quantum efficiency and light extraction efficiency, you will get the light external quantum efficiency. And as the efficiency in ideal condition, what is that? Ideal condition, the efficiency is 1. That means 1, if we give 1 electron hole pair recombination, that gives you the 1 photon. But in ideal case, it should not be that, it should be less than that. And if we multiply so many components whose value are less than 1, so obviously the multiplication of the all components will be very, very less than 1. So if any of the components is less, then the efficiency of the device will go less. So that I represent that in ideal condition for LED particularly, we check that 1 photon out of 1 electron in. But in actual case, this external quantum efficiency, that is the multiplication of injection efficiency, internal quantum efficiency, light extraction efficiency. And after that, if we package that device, then again, it depends on the packaging efficiency. This is the wall plug efficiency. This is external efficiency multiplied by the electrical efficiency. So injection, if we consider that in internal quantum efficiency, that is very much dependent on the material quality and device structure. And what we have, now we are discussing now that LED, typical LED structure is the multi-quantum well LED structure. And earlier I understand that you have gone through that PN junction diode. LED is also another diode. But it is not simple PN junction diode. Obviously, simple PN junction diode with that material will also emit light, but not with that much efficiency. For the improvement of efficiency, we have to go for that quantum well based LED. And further improvement of the light, we have to go for that multiple quantum efficiency, multiple quantum well region for that device. Now, what we have discussed, the gallium nitride is the base material. So if we consider that this is the gallium nitride region, and if we incorporate aluminum composition, what will happen? The band gap increases. So this is the band gap of aluminum gallium nitride. So this is N side, this is P side. With P doping of aluminum gallium nitride region, this is gallium nitride quantum well region, and it forms the quantum well because its band gap is low compared to those two barriers. So these two areas are will act as the barrier, and this is the quantum well. So with when these electrons will activate, so it will go to that valence band to conduction band here, and after certain time it will recombine electron hole recombination that will produce the light energy. But here the property of the gallium nitride material is piezoelectric. And for the piezoelectric material, it is having the formation of certain dipole, spontaneous, and even if it is, even if we don't apply voltage, and if we apply voltage, further band bending will be there. So if band bends are there, so it will not straight those edges of valence band and conduction band, those bends. So if bends, obviously whatever the electrons, carriers will be generating, that will go towards the lower energy state. So it will go towards this area and here in this area. And for the recombination, the overlap of electrons wave function and overlap of whole wave function will not matching. So if that does not match, then full radiative recombination will not be there. So certain portion of non-radiative recombination in terms of photonic transition will be there. So those will be in the form of heat. So what do we have to do? We have to narrow down this quantum well region so that the separation, this x-axis separation will be less, so that the overlap of electron and whole wave function will be much more. But again, what will be the problem? If this thickness is less, then the number of electrons within this well will be less, and the amount of light is being generated, that is depending on the number of electron hole recombination. So what to do? In the active region, we just go for that lesser and lesser thickness of well region, around 2 to 3 nanometer. But in the active region, we use multiple quantum well region. So the overlap of this electron and hole wave function will be there, will be much more, and at the same time number of wells will be there, so number of those will generate or multiple the intensity of the light. So those things are explained, that high defect density and p-doping reduces the injection efficiency, and internal quantum efficiency is reduced due to polarization, and that effects causes droop. Droop is another term that if we go for higher and higher electrical drive, and much more will get the light output. But if we go increase and increase the electrical drive, the light output will be almost saturating. So it is not linear, and after that the efficiency in fact decreases with if we increase the current density. So with higher and higher current density, the efficiency then decreases, and that is called the droop, which we don't want. We want that with the increase of current density, we need much more light output. So how to compensate that droop? So that is also another criteria. And the other thing also, that poor extraction efficiency, how that is depending on the refractive index of those materials. So we'll discuss wider way that in general, when we fabricate the gallium nitride based LED devices, we use sapphire substrate as a substrate, and then gallium nitride material, and this is the N region, and within that is the active region. Active region means number of wells and barriers will be there from where the light is being generated, and then P region of gallium nitride, then light output here. So where we need the light? We need light outside of the device here, and where the light is being generated? In this region within the device. And what are the refractive index? This refractive index of 1.7 sapphire material, and gallium nitride is having refractive index around 2.5, and outside refractive index is 1. So what happens? So light is being generated here, and when it is being propagated, light is propagating from higher refractive index medium to lower refractive index medium. So when light propagates from high refractive index medium to low refractive index medium, what happens? It goes away from the normal. So after certain critical angle, again it reflects back to the medium. So only certain portion, so that is called the acceptance angle or acceptance cone. So certain light will be the output in that area, and maximum portion of the light will be propagating within this material itself, back and forth, due to total internal reflection. So but that is not needed. We need one thing, we need light here, and what we are getting, we are getting light output here, but a certain portion, maximum light is being generated here and propagating here. We don't need, and in additionally, that will generate heat also. That propagation of light that generates heat within that material, and obviously, eventually that will deteriorate the performance of the device. So what to do in that case? Oh, sure. So that is the Drup equation. So this is one typical structure of LED. So what I mentioned, that we take that sapphire substrate, again depending on the growth of that substrate, this is the 001 C plane sapphire substrate. On top of that, we grow the material gallium nitride as the buffer material. Why buffer material?
How should the sapphire orientation be? Means like 001 or 101?
So in when you consider that crystal lattice, the growth of that crystal lattice is depending on the structure, and this is the Miller indices. Okay, so these are the Miller indices. Depending on the growth and depending on the direction of the growth and plane of the growth, we can calculate, we can estimate what are those. So just like what type of structure it is. If it is hexagonal structure, wood-joint structure, basic structure is diamond structure or cubic structure. Again, within the cubic structure, there are few things that whether it is a body-centered structure or centered kind of thing. From here, the light. मूव तो नहीं कर, बैटरी डाउन तो नहीं. So depending on the structure of that material and the growth of that, we can consider that which is the plane we are using. This is called the C plane of sapphire substrate, and basically this is the hexagonal structure. Hexagonal. So if we check the Miller indices of that one, that in the top, as we grow of that hexagonal structure, and in the growth is on the top side, so this is the C plane. But in other direction also we can grow the material. So depending on the growth of that material on other sides, we can have different plane of sapphire. M plane, or this is C plane, another plane is there, M plane, another plane is A plane are there. So this is the C plane we are using because this is in general, and without any difficulty we can grow that material. But the difficulty or the problem is there, this on top of sapphire C, if we C plane sapphire, if we grow the gallium nitride material, it will be spontaneous, it is having spontaneous polarization or piezoelectric material. If we grow the material on top of M-plane sapphire, so that is quite non-polar. So in that case, that the polarizability or the polarization property of this gallium nitride material might be less. So for various applications, we have to select the substrate. But again, the cost matters. So if we consider that C-plane, it is very much cost effective in terms instead of other M-plane or A-plane. Yeah. In that direction, if we grow that direction, so M-plane will grow. And after that, we cut and we make the substrate and we use that one. And then we go for that gallium nitride buffer before we go for that N gallium nitride growth. Then why buffer? We can straightforward go for gallium nitride N. This is because that lattice matching. The lattice constant of sapphire does not match with gallium nitride. So we have to go for that certain buffer material where we can, this so that mainly this buffer is particularly for that making the interface area in between gallium nitride and sapphire for matching the lattice constant. So we go for that N-GaN with silicon doping. Then we go for that multiple quantum well and barrier region. Quantum well if we incorporate indium composition, and then without indium composition, state gallium nitride will act as barrier. We can incorporate 5 to 10 number of quantum well and barrier, and after that certain region of EVL kind of thing, and then we go for that p-type gallium nitride. From here we make the contact. So p contact we make from here, and n contact we make from here. Again, so these p contact and n contact both are metal contact. But you see that these metal are different for p contact and different from n contact. Again, that is depending on the what is the material, what is the electron affinity of that material. So what combination we need the metal semiconductor for that interconnection. And obviously, we need to go for that ohmic contact for that P as well as N. But in general, if we go for that metal semiconductor connection, it will be Schottky contact, which is not ohmic. So we have to convert the Schottky connection into the ohmic connection by proper annealing in particular environment. So those are the things. So here, that light extraction, what I was mentioning. So this is the thing that see, for example, light here, it is the denser medium, it is lighter medium. And when light goes from denser to lighter medium, it goes away from the normal. And after certain angle, it will go towards interface, and beyond that, it will back to that medium itself. So that creates the total internal reflection. So light will be extracted in that area only from that region, so outside. So for that corresponding to that area, that is called the escape cone. And the light beyond that one angle will be propagating back and forth within this area itself. So that is deteriorating the property of that one. So those are the refractive index, that one, of gallium nitride and sapphire. And if we check the values, that whatever the light is being generated here in the active region, around 6% is being extracted in the air here. And so rest 94% being trapped within the medium. And what are the components? Around 66% within the gallium nitride material and rest 22% within the sapphire substrate here and rest 6% from that area. So how to maximize that portion and how to minimize this portion so that the increase of light extraction will be much more. So this is the region from where the light is being generated. So one possibility is there, whatever the escape cone is there. So one possibility is there how to increase that escape cone. Because that escape cone is depending on the refractive index contrast 2.5 and 1. Okay. So if we incorporate certain material whose refractive index in between these two, 1 and 2.5 here, so escape cone will be increased to some extent. The other thing is whatever the light is being reflected from here, if we put some reflector there, so light will be reflected back from that portion, again it will be coming towards that. So if we incorporate certain things, certain reflector, maybe aluminum reflector we put here, so whatever the light was extracted in that other direction will be reflected back, and ultimately that will go in that direction. And if we incorporate another material of refractive index 1.5, which is silica. Silica is readily available. If we incorporate that of certain thickness, so obviously the acceptance cone will be increased, so light will be much more, light will be extracted in that area. But again, there is a trade-off, because if the thickness of that material is there, so for that thickness itself, whatever the light is being extracted, that will be absorbed in that area. So there will be a trade-off, but we can increase that one. So that is one thing. So we can increase that portion to make it combine in that area. But again, whatever the light is being propagated in that area, that will be propagating. So how to minimize that one? That can be minimized if we incorporate certain periodic or aperiodic structure, nanostructure or microstructure here. So again, we can design that type of structure, and whatever the emission we need, based on that we can net that periodicity or aperiodicity depending on the bandwidth what we need. So those wavelength components will not propagate in that direction, rather that will be emitted in that direction. But again, the problem is that if we go for that nanostructure or microstructure here, we need also the contact, P contact or N contact. So if we go for that contact, after that, the resistance between metal and semiconductor will be much more. So that will deteriorate the performance. So what we need to do, we have to go for that selective etching of that periodic structure. So wherever the contact is there, we need not go for this type of periodic structure or aperiodic structure. So suppose here it is a plane structure, we have to go for that contact formation here, and the rest of the portion, emission area, we have to go for this area. So it will be like that. So here the contact portion will be there, P contact, here N contact, and from here the emission will happen there, this type of corrugated structure we can form to increase the light. So it is also called the photonic crystals type of structure, depending on the periodicity, if it is periodic, aperiodic. If it is periodic, particular wavelength we can design, that wavelength will not propagate, will emit that one. If it is a bit aperiodic, the bandwidth of that emission will increase. So those are depending on what we need. But the thing is, we can increase the efficiency, light extraction efficiency around 75%. The other also, that the sapphire substrate in the sapphire substrate itself, if it is patterned, so whatever the light is going in that direction, that will be reflected back. So that will not come to that sapphire substrate. So that will be reflected back from the top edge of the sapphire substrate itself. So that is also another point we can consider to increase the light extraction efficiency. So this is the structure kind of thing. This is one thing, one structure. This is lateral structure. In general, we have to etch that portion in, and P contact, N contact are there. And when we drive, the current will flow from that side to that side. And in this area, in this device, the active region, in the active region also, the current will pass through lateral. So that's why it is called the lateral LED. But we can fabricate another type of device where the P contact and N contact in the opposite direction. And the current will flow from P to N vertically. So here there is no path to flow the current laterally. So it is called vertical LED. And obviously, from the emission area itself as well as the current crowding. Here the current crowding effect, so that is another difficult property, that here current crowding will be there, and much more current density we cannot flow. If we flow much more current density, the device will damage. Here we can flow much more current density as well. So those are few structures and how we can, how is the performance increase. So this is the one typical structure, that this is P contact will form, this is N contact, and a certain transparent conducting layer will form, and this is the emission area. And this is no photonic crystal, no periodic structure is there. And here we form that full photonic crystal, but the contact within the photonic crystal itself. And the third is the selective photonic crystal, but the contact is there, no photonic crystal. So what is the performance? See, so this black one is the no photonic crystal, that light output is less, and red one, selected photonic crystal, is the maximum one. Blue, this is the in between, because here the contact resistance will decrease the performance. Some examples that photonic crystal type of structure we can incorporate using micro lens also. This type of micro lens array, polystyrene or silica microspheres are available. We can deposit layer and we can etch that one, so that micro fabrication is already there on top of structure, and we can get the light output much more. We can go for various type of structures as well on top of this. This is, I will not go into detail, but in general, if we go for that, this type of structure on top of the emission area, the light emission extraction efficiency will increase. So various types of, it is periodic structure in form of hexagonal, in form of rectangular, in form of chessboard we can have, and various designs are there how light extraction efficiency increased. Now in terms of electrode design as well, because this is the emission area, and this is the P contact, and this is the N contact, and yellow portion of the emission area. If the device size is very low, that means the area is 350 micron by 350 micron, then we can consider this type of structure. This is called the pad type of structure. But if the area of the device size, which is in general 1 millimeter by 1 millimeter, we cannot use this type of pad structure. In that case, what happens? Because current flows from that region to this region, and the current density will be much more in that area, and in between that will be very less. So uniformity of current density will not be there. If the current density uniformity is not there, so light uniformity from the emission area will not be there. So what we need to do, we have to go for that, this type of finger structure. So here, very thin layer of P and N interdigitated structure we can consider, so that the current is being uniformed within this emission. All this green area will be, emission area will be uniform, because the distance from P to N will not be that much, so that the current density will decrease. So we have to consider this type of structure. So this is the cross-sectional structure. Various type of structures are there, and we can, depending on that, this is the current distribution, this is the light extraction, and we can see that these two are proportional. And obviously we have to check that the area of emission will be around or more than 80%. So there are a few criteria here. Again, this is certain structure for UV LEDs, in general LED, but UV LED we have to go for that AlGaN instead of InGaN. For AlGaN, again, the structure will be similar, but the quantum oil structure and various structure will be all AlGaN or GaN-AlGaN. So depending on what emission wavelength we need. So in this case, quantum oil region aluminum composition is 47% and barrier 62%. So barrier aluminum composition more means band gap high. So that can act as barrier, and low means that can act as oil. And depending on the aluminum composition, we can have the emission wavelength. So in this case, emission wavelength is around 265, which is very much required for sanitization purposes, particularly UVC region. So we can design accordingly, and obviously we can fabricate. So here are few designs that how we can minimize the droop. So what I called droop, that with the current density increases, the internal quantum efficiency increases, but after certain level, it then decreases. So it is supposed, it should not happen to do that, but that happens due to this polarization property. How to minimize that one? Because what we need, that we have to go for that high light output power. So we need to operate in higher current, but in order to operate in higher current, the efficiency will go less. So although we will get a little bit higher light output, but efficiency is less. So in terms of non-radiative recombination, it will be much more. So heat component will be much more. So if we operate the device at higher current density for higher time, the possibility of damaging that device will be much more if we don't go for that efficiency droop minimum. So this is one design, and see here. So this is the almost no droop. So this is the first design. After certain current density, the efficiency, internal current, quantum efficiency decreases there. And if we optimize that one, so this is optimized. So you see that with the increase of current density, there is no decrease of internal quantum efficiency. So that kind of design we can have. So here you see that aluminum composition in the oil region 47%, because that we need depending on what emission wavelength we need, and barrier is the other 0.62%. And in addition to that, there are various superlative structures and electron blocking layer we have considered to optimize that drooping. The other thing is, particularly for UV LED, light is being emitted in the UV region. But if we use the AlGaN material absorbs the light. So if this type of structure is there, and in blue LED it is fine, light is being generated, and here it is GaN, light is, and this material is transparent to that wavelength, so light will be transmitted in that region. But in case of UV, so P-GaN is here, the barriers are also AlGaN, and the layer of AlGaN will be there. but those algae are not transparent to the UV light. So UV light, whatever being generated within the device, those will be absorbed if we go for that transmission of light in that direction. So what can be done in that case? We can go for that flip chip type of kind of bonding, because on the other side we can narrow down the algan layer, and because on the other area gallium nitride portion are there and sapphire portion is there. So sapphire portion is transparent, very much transparent. So we flip the chip, we just flip the chip and bond in that side. So light will be extracted not in that direction, light will be extracted in that direction. So it will just flip that and the light will be extracted in that direction. So that can be, that we have to do for the UV LED. This is another possibility. If we use that 3-nitride gallium nitride material, and if we use for solar cell, we can use the whole range of solar spectrum. So those are the solar spectrum, and if we incorporate that alum composition to indium composition, you can see that from 6.1 electron volt to 0.67 electron volt we can consider. So theoretically, we can cover the whole solar spectrum to increase the efficiency of the solar cell. Although there is practically some problem because of the indium incorporation or aluminum incorporation in that. Gallium nitride based HEMT is another device which is high electron mobility transistor. We can use the structures in such a way, a very thin layer of 2D electron gas formed in between this substrate. And in this layer, the conduction of that current will be much more. And that can operate as the high electron mobility transistor and can be it can be applied for various sensing applications, in high power switching applications, high power amplification applications as well. UV detector as well, because if it is this material can be used for LED, it can be used for detector application as well. On the other side, so the thing is the light is being captured in that area, and according to that the current will be generated. So that's certain structure, and that can also be done. This is one example how to lowering the temperature if we use the flip chip of that device packaging, particularly for UV LED. So how was the time? Okay. So this is on theoretical aspect and design I have considered. Now I am giving few examples of what we have fabricated after design in our laboratory also. So very briefly I am mentioning that this is the overall flowchart for the gallium nitride, indium gallium nitride, blue-white LED device fabrication. And the flowchart is almost similar for UV LEDs as well. And one basic advantage we have that we have our MOCVD reactor, and that reactor, through that reactor, we can grow the gallium nitride based material. So if we first design that structure that we have discussed, and after that design, we grow that material by using gallium MOCVD reactor, that is metallo-organic chemical vapor deposition system. And after that, so based on the structure and electrode design, we make the mask, and then we go for that photolithography first level photolithography for mesa etching. Because what I have shown that the structure of the device, that P side top and N side the bottom. So we have to go for patterning of P and N, and according to that we have to etch that N region to get the N contact. So after etching that N region, we have to go for that contact formation in that N, so we can get the N contact. Again, we have to go for further photolithography selected portion of the P, we have to go for that P contact. So various sections are there. So photolithography for N contact, then titanium, aluminum, nickel, gold N contact formation, then annealing for ohmic contact making, then photolithography for P contact, then another nickel gold P contact formation, then photolithography for gold plating. Then after that, we have to go for that dicing. This is electroplating. After electroplating, we have to go for that another photolithography for transparent layer, transparent conducting layer in the emission area. Very thin layer of nickel gold transparent layer we deposit. And then again, we have to go for that very thin layer of oxide, that is for isolation or air coating. And again, we have to go for photolithography etching, then wafer thinning in the back side. Then we have to dice that as per the device size. So we grow in wafer, and after that we dice that in terms of the device size. And then we go for that bonding and the packaging. After packaging, we will go for that characterization, that what is the emission, whether we are getting that in terms of our design or not. And for white light, we have to go for that coating of yellow phosphor on top of blue light. So we go for that yellow phosphor coating. That is another optimization. What is the phosphor concentration? What should be the thickness of yellow phosphor? We have to mix that yellow phosphor with some elastic material, polymer material, and what should be a thickness? All those things we have to optimize so that the white light, exact white light we can get. This is something that this is the structure. This is the pattern, sapphire substrate. We can consider some results that what we are getting. And this type of periodic structure on top of PGAN, on top side, we can go so that the further we can get a better result in terms of light. So those are the light output in that area. So this is in general that what we are getting in blue light, and this is the yellow phosphor combination. And if we combine this yellow with blue, we'll get white. And in terms of color chromaticity, those will be the position. So white position will be here. So that the color temperature will be around pure white, it should be around 5,000 to 6,500 Kelvin. So these are the fabricated chip. And what we have tested blue LED in LED characterization system, and the emission of the blue light and the position of the blue light here. And now after that, after yellow phosphor coating, we'll get the yellow light. Again, we can test in the chamber, goniometric chamber, LED characterization system. And this is the blue combination and with yellow light combination. And this is the point where we are getting the white light. So this is another device. Lasers also we have fabricated 980 nanometer laser on indium gallium arsenide. That is for another application. It is also another semiconductor and ternary semiconductor. And this is the individual laser chip. This is the length, and this is one side we can have to go for that high reflection coating. Another side we have to go for that low reflection coating, so that emission will be from the low reflective, coating side. And after that one, each individual, here the laser bar, number of LED chips are there. Each individual will be laser chip, and that will be packaged in butterfly package. And that was used particularly for erbium doped fiber amplifier application. Few trends that what I mentioned, that this is the lateral LED where P contact, N contact are there. Current will be flowing in that direction. So that is, there is the problem of current crowding. But if we go for that vertical LED kind of thing here, or flip chip kind of thing, that the current or the light extraction from the top side, the light extraction will be much more. The other point is that vertical LED formation, that gallium nitride on top of sapphire substrate will grow. But after growth of that material, if we use that laser light and if we break the interface between gallium nitride and sapphire, because the excimer laser, what we are using, that is transparent in that sapphire, but that is being absorbed in that gallium nitride material. So in the interface that will form, gallium nitride will form gallium material and nitrogen gas. So that will break after certain chemical treatment, it will be like that. So sapphire substrate will be removed, and here that will new substrate is there, and we will fabricate the device on the other side, top side, bottom. So it will be like that. In that case, vertical LED current will flow in the vertical direction, and there much more light output will be there. The LED can be operated in various very high power. So those are few examples of what we have. So what I mentioned that the area of UV LEDs, and if we increase, this is a year, and quantum efficiency what being achieved. So with time, obviously the efficiency is being increased, but if we see the market, so this is the huge market for UVC particularly, and this is the efficiency with wavelength. So see that if we increase the wavelength, the efficiency is higher and higher, but where we need much more requirement, particularly in the UVC region, the efficiency is quite less, within 10% level, up to 300. So you see that within 10% external quantum efficiency. So what we are projecting the efficiency, obviously with time, so this is the real time what we have achieved, but with time we are progressing that the efficiency will be more, and it will reach around 20%, by the year of 25. And you see that this is 310, 285, 360, 265. So as the wavelength is going below, the efficiency is low. But although we are trying to converge with the time. Various ways of working in the area of UV LEDs. So, any question, particularly for this topic? Are you okay with the other specific component?
Which one is a Schottky contactor, which one is a like Ohmic contact? So how we identify after the constructing a contacts?
Is linear. IV characteristics is linear. For Schottky contact, it is not linear. It is non-linear. That is the main testing. So after formation of that metal semiconductor junction, we can go for testing. We have to go for proper annealing of that one in particular environment, either oxygen or nitrogen or certain condition and certain temperature for certain time. We have to anneal that so that the Ohmic contact. Ohmic contact, in general, we mean to say that IV characteristics is linear. And not only that, the contact resistance will be as low as possible. We have to go for.
Suppose we want to grow a GAN on a sapphire surface. So there is no epi layer will generate in between, or it means directly we will grow a GAN on a sapphire surface.
When you grow the material, see, there are two terms. One is deposition, another is epi-layer formation. Epi-layer formation means we need to, with the deposition, we need to uh, uh, fulfill the condition of lattice matching. So as the lattice constant of sapphire and gallium nitride is very much different, so that's why we need buffer material, where the buffer material acts as to minimize the defect density creation. So if we go certain amount of buffer layer with certain thickness, after that we can check that there is on top of that we will, whatever we are growing, that will be the epi layer. Because after certain level thickness of gallium nitride formation, so the lattice constant will be gallium nitride, and we are growing the material of gallium nitride on top of that. So that's why the buffer requirement. And okay, very briefly, I just. So those are the passive devices. I am not going into the detail because those are components and devices where it is required in various ways. I was thinking of explaining particularly three devices. One is coupler, splitter, and filter, and we'll cover the all communication components, specific components. Because suppose we want to transmit certain wavelengths, number of wavelengths, and we want to combine that one. So lambda 1, lambda 2, lambda n. So coupler means it combines all the wavelengths. We can fabricate that one. And the other device is there, that optical power splitter. So certain light is there, and we want to use the same light for different devices. And whatever the intensity of light is there, we are getting, that may be much more sufficient. So if we divide those light intensity to operate various number of devices, so we can keep all the wavelengths, but we need to divide the devices light intensity. So those devices are splitter, and again all those are going certain areas, and if we need to again filter out certain wavelengths and to get certain wavelengths, so for that are the filter. So lambda 1, lambda 2. So we start with lambda 1, lambda 2, lambda n. We combine those, we divide those in terms of power level, and then again we filter it out, kind of thing. So this is one kind of thing, optical splitter, that we can, whatever the light is coming, it is being tapered and will be branching in two ways. And we can branch in different ways, in three ways. Three branch, we can go for 1 cross 2, 2 cross 4, 4 cross 8 kind of thing, depending on the requirement. What are the technology compatible design for that? So for that, we have to go for that tapering of that. And then up to what area we need to go for that tapering, branching, all these things we need to consider. If we consider this is the black box, and this is the input and output, 1 cross 2, 1 cross 4, 1 cross 8, we can consider. So this is symmetric type of Y branch structure. Various ways we can design. So if this is input 1 cross 2, 2 cross 4, 4 cross 8. So what are the ideal loss there? So what are the criteria if we consider the fabrication of this type of power splitter? So one is the insertion loss. So ideally it will be 3 dB insertion, 9 dB insertion loss. Why? Because this, whatever the power is being divided here, so 3 dB being divided, and again half of half. So here we are getting 6 dB, and after that again 3 dB means total 9 dB, ideal. So if it is more than that, so then we need to optimize those things. So this is another concept of multiplexer, demultiplexer, particularly combine the number of wavelengths or decoupling the wavelengths. Just for a quick through, so those are the points that how decoupled and coupled. Those various wavelengths there, what are the parameters for that one? We can design the symmetric so that the same device can be used as multiplexer as well as demultiplexer. This is one thing that is long period waveguide grading, particularly for filter. If we go for particular waveguide, have certain corrugation on top of that, we can, depending on the thickness, periodicity, structure, we can check to pass certain wavelengths and we can drop certain wavelengths. So this is design of those splitter, simulation, and after fabrication. Those are the this is the design simulation results. The insertion loss, all are C, all 9 ports are having around 9.2 dB kind of thing. And we can check with TE mode and TM mode, obviously. And for TE mode and TM mode, the polarization dependent loss will be different. It will give the polarization dependent loss. And if those are the uniform vibrance, then in all outputs, 8 outputs will be the same. But in ideal case, that will not be. So how much non-uniformity will be there? We can design also, we can fabricate. So after design and after fabrication, what are the results we are getting? So based on the design, we go for that mask fabrication here. And if we very briefly go for fabrication steps, so silicon substrate, on top of that, this is the undercladding, and this is the guiding region where the device is being fabricated. On top of that, we go for that photoresist coating. And then we go for that photolithography, use the mask photolithography. So it comes as a soften, and those portions will be hardened depending on the type of photoresist we are using. So after that, it will be there, photoresist will be there, and will be removed from there, and we will go for that metallization of that one. So on top of that, metallizations will be there, and we will go for that lift off, so that all the portions will be removed here and here, only these portions will be attached here. And now we will go for etching. So this portion will be etched from here, here, and those portions will not be etched because the metal is there. And after that, we'll remove that metal through some chemical. So we'll get this type of structure, and then we remove that one, and on top of that, we'll go for that another cladding of oxide. So undercladding is there, this is guiding layer, and on top of that, cladding, overcladding layer. So it is almost similar to optical fiber, but not circular, but in guided in rectangular waveguide region. So it will be like that. And after that, we go for that dicing and the packaging, and what I told that whatever the integrated component we made, and we go for that polishing of facet, and we incorporate with that optical fiber into that, couple into that one, and here the 8 optical fibers coupled, so 8 light outputs are there. We can get 8 outputs out of 1 input. So this is one typical schematic, and after the packaging it will be like that. Similarly for the other devices. So got a glimpse of how the photonic components, similar fabrication process for other photonic passive components will be there. Any question on that? The problem of fiber optic splitter will be one thing. We have to go for fabrication of each fiber optic splitter one by one. Here, we can go for mass production, one thing. We can make mask and we can fabricate number of devices. The other thing is, if we fabricate fiber-based splitter, so the uniformity or non-uniformity of each coupler, 1 by 2, 2 by 4, 4 by 8, may not be decided. So at any point, it may be different. But here, as per the design, we can optimize the design so that the uniformity of all outputs will be as minimum as possible, and after that we can fabricate. That may not be possible in fiber-based. Other is also stability. Coaxial cable. Uh, Coaxial cable, the formation or the structure of coaxial cable and fiber optic cable is similar, but the material is different, and obviously signal is also different. They are also here in optical fiber, the core region is there and cladding region is there, and light is being propagated through total internal reflection principle, and the signal is being propagated is the light signal. And in coaxial cable, that is electrical signal, area is much more, and yeah, in structure wise, that is same, but the signal propagation and bandwidth, everything will be different. Okay, thank you.
Thank you very much, sir, for this enlightening session in the domain of photonic devices. Now, I would like to request FDP coordinator Mr. Rajesh Singh Shekhawat to honor our distinguished speaker with a token of love.